You know that feeling when you're looking at a big grid of data, maybe a spreadsheet, and you just think, I wish I could just flip this whole thing on its side? Turn all the rows into columns and all the columns into rows? Well, that simple flip is a really fundamental move in programming and data science, and today we are going to crack the code on exactly how to do it.
So what you're seeing right here, that's the whole idea in a nutshell. It's a matrix transpose. Just look at how the elements in that first row of matrix A become the first column in its transpose. We're going to break down exactly how this visual trick works, from the basic concept right down to the actual code.
All right, so here's our game plan. First, we'll nail down what a transpose actually is. Then we'll get into the secret sauce, that core ij to ji swap. After that, we'll map out a 4-step algorithm, bring it to life with some C code, and then wrap up with a look at performance and the key things you need to remember.
Okay, first things first, let's really get a handle on the concept. What are we really doing when we transpose a matrix? You'd be surprised how important this one little flip is for everything from machine learning to 3D graphics.
This right here is the perfect example. On the left, you see a matrix with 2 rows and 3 columns, right? A 2 by 3. After we do the transpose, look what happens on the right. It's become a 3 by 2 matrix. The most important thing to see here is that the dimensions themselves literally flip. The number of rows becomes the new number of columns, and the number of columns becomes the new number of rows.
So yeah, the formal definition is pretty straightforward. A transpose is just the operation of swapping the rows and columns. And you'll pretty much always see it written with that little superscript T next to the matrix name. That's just the universal sign for transpose. Simple idea, simple notation.
And now, let's pull back the curtain and see the magic. It all boils down to one single, incredibly simple rule that tells every single number exactly where it needs to go.
This is it. This is the golden rule, an element that's sitting in row I and column J of your original matrix. It's going to end up in row J and column I of the new transposed matrix. You just swap the indices. That's the entire logic right there in one little formula.
And this table makes that rule totally concrete. Let's say we have an element at index 0, 2. In programmer speak, that's the first row, third column. We just apply our rule, swap the numbers, and it moves to 0, 2 in the new matrix, the third row, first column. See? It's a perfect, clean swap. Okay, now let's turn that logic into an actual plan. Because, before you write any code, it's always a good idea to lay out a clear step-by-step recipe, an algorithm. And our recipe is just 4 easy steps. 1, we gotta know how big the matrix is. 2, we need to actually fill it up with our data. 3, and this is the big one, we'll use a couple of loops to apply that golden rule to every single element. And then 4, we'll print out the results so we can admire our work.
All right, enough theory. Time to get our hands dirty. Let's translate that 4-step plan into some real working C code and see what it actually looks like.
So the first chunk of our program is all about setup. We declare 2 2D arrays, one for the original matrix and one for the transpose. Then we ask the user, hey, how many rows and columns? And once we know that, we use a pair of nested for loops to go through cell by cell and get all the numbers from the user.
Now that we've got our data loaded up, we've arrived at the heart of the whole program, the part that actually does the transpose.
And here it is. This is the C code that makes our golden rule a reality. It's just one line, sitting inside 2 for loops. The loops go through every element of the original matrix. And for each one, this line says, okay, take the value at matrix ij and copy it over to the transpose matrix at the swapped position, jj. It's so simple, but that's what does all the heavy lifting. Last but not least, we have to show the result. And pay close attention here because this is a really important detail. Look at the loops we use for printing. The outer loop now goes up to C, the original number of columns, and the inner loop goes up to R, the original number of rows. We have to use those new flip dimensions to print it out correctly. Oh, and just a quick side note on a special case. What if your matrix is a square? Same number of rows and columns, like a 2 by 2 or a 3 by 3? Well, its transpose will have the exact same dimensions. The shape of the grid doesn't change, but all the elements that aren't on that main diagonal, they still swap places. So, we've built it, we've run it, but how fast is it? And what are the absolute key things you need to walk away with? Let's wrap this all up.
You might see this big O notation and think it looks kind of complicated, but it's really not. O of n times m is just a fancy way of saying that the time it takes to run our program is directly tied to the number of elements in the matrix. To transpose it, we have to visit every single cell exactly one time. No more, no less. It's as efficient as you can get.
So, if you remember just 4 things from all this, make it these. 1. Transposing is just swapping rows and columns. 2. The core logic is a simple index flip. 3. The code just needs 2 matrices and some nested loops. And 4. It's a fast operation whose speed depends directly on how big your data is.
And look, this isn't just some abstract programming puzzle. This is a fundamental tool that's used everywhere, from analyzing huge data sets to rotating 3D models in video games. So now that you know exactly how it works under the hood, the real question is, what are you going to use it for?